Assalamualaikum warahmatullahi wabarakatuh. Good morning, good afternoon, honorable judges of the 7th International Conference on Chemistry and Material Sciences 2025, hosted by Universitas Teknologi Mara, Malaysia. First, I would like to express my sincere gratitude to the organizing committee for their exceptional efforts in bringing together this remarkable gathering of minds. Allow me to introduce myself. My name is Adelia Salma Septiani, and I will be presenting my research about research recovery from waste. Indonesia is the world's largest archipelagic nation with more than 17,000 islands, giving it tremendous natural resources potential, particularly for salt productions. With the world's longest coastline and a supporting tropical climate, Indonesia has a comparative advantage in salt production through the natural evaporation process. One of the largest salt productions in Indonesia regions is Madura Islands in East Java, which has served as a traditional salt production center for many years, with salt fields covering thousands of hectares. The salt productions process in Indonesia generates a byproduct called as bitterns, which is a concentrated salt solution from seawaters that remains after salt crystallizations. Bitterns contains various important minerals, especially magnesium chloride, in high concentrations ranging from 0.30% to 6.26%, and also until now, bitters has often been considered a waste product from salt production that is not optimally utilized. Despite its mineral content having a great potentials for various industrial applications. In this research, I will further explore magnesium chloride as a coagulant as a form of natural resources recovery. Let me start with a significant milestone. On 2 October 2009, Indonesian batik received prestigious recognition from UNESCO as a masterpiece of the oral and intangible heritage of humanity. Following this recognition, we've witnessed remarkable growth the global batik market between 2000s and 2014. However, this growth comes with environmental challenge. The literature shows about the 200 cubic meters of fresh water for the production. Significantly, 90% of these waters end up as wastewaters. The primary environmental concern is the only 5% of days for the coloring process, while 95% remains in the wastewaters. The batik production use several types of dyes. One of the specific example is remasol, which is frequently used in our batik productions. Remasol also has a characteristic such as easy to dissolve, high resistant in various environmental challenges such as pH, temperature, aerobic degradation, and also UV photodegradations. So the consequence is the turbidity in our river flow. This cloudy water reduces the sunlight penetration, disrupting the photosynthetic activities and also decreasing oxygen levels. This adversely affect aquatic life such as declining biodiversity and also fish deaths. Even in the soil productivity along these water bodies is suffering as well. To address these issues, I evaluate three main treatment approach, which you can see illustrated on the slides. The several methods, such as electrocoagulation, have been stated to help the dye removal efficiency, but these methods have several limitations, such as require a long process time to be effective, high capital and operational costs. On the other hand, the industry also use the biological methods such as artificial wetland, but these methods also have several limitations such as require a long time to be effective, require a large land area for the large scale application. So the alternative process that industry can use is the coagulation process. Why? Because this process provide a several advantages such as it doesn't require a long time to be effective, it doesn't require a large land area for the large scale application, and also the capital and operational cost is relatively cheap than other. Moving on to the literature review, I examined key comparative studies by Mikoto and also Hussein and also Farma. This table shows the maximum dye removal efficiency in the different coagulants. As you can see, the results about the magnesium chloride achieve the highest dye removal efficiency than others, and also magnesium chloride less expensive, easy to obtain, and absolutely agents of research recovery for these topics. I identified a gap in the previous studies in that type of dye used was acid dye, which is really used in our batik productions in Indonesia because it's not suitable for clothing fibers in tropical countries like Indonesia. That's why, based on these limitations, my studies will focus on the effect of coagulant dosage, pH, and coagulation speed on the removal of ramazoyl FG using magnesium chloride. Based on the backgrounds, this study formulates several problem statements, including what is the effect of magnesium chloride dosage on the removal efficiency of ramazoyl FG, what is the effect of the pH solutions, what is the effect of coagulation speed on the removal efficiency of ramazoyl FG, and also for the scope of this study, including the test parameter studied was the ramazoyl FG, the removal efficiency, coagulation time is a minute, and flocculation is carried out speed of 50 rpm for 10 minutes and a settling time of 30 minutes. And for the quantitative analysis for measure concentrations of ramazoyl FG and maximum wavelengths using spectrophotometer UV phase. Next, the research objective, including the studying the effect of magnesium chloride dosage, studying the effect of pH solutions, studying the effect of coagulation speed on the removal efficiency of ramazoyl FG, and also for the benefit of the studies about the studies demonstrate the optimal performance of magnesium chloride as a coagulant for removing ramazoyl FG, and also these findings provides a foundation for developing coagulation flocculation treatment methods for various batik dyes commonly used in Indonesia. This studies was conducted from March until June 2025 at Analytical Chemistry Laboratory of Department Chemistry, Faculty of Mathematics and Natural Science, Brawijaya University, Malang. Move to the research stages. This method consists of five main stages representations on these flowcharts. For the first stages about the selection tools and the materials, the second stages preparations of the solutions and also determinations of magnesium wavelengths and the standard calibration curve of ramazoyl FG, and fourth stages about the research parameters, and the last stages about the data analysis. These slides about the tools and the material was used for these studies. Next, about the preparations of the solutions, I divided into four stages, such as preparations of ramazoyl FG stock solutions, 100 milligram per liters, preparations of ramazoyl FG solution, 30 milligram per liters, and also preparations of the solution hydrochloric acids, and also preparations of zero point 0.5 molar sodium hydroxide solutions. On these slides, the research procedure for determining the maximum wavelengths in the range 300 until 600 nanometers, and also determinations of the standard curve calibration for amazole at the concentration 0, 10, 12, 30, 40, 50 milligram per liters. This slides about the preparations determinations the effect of dosage, which is the sample solution was prepared at the concentrations 30 milligram per liters, and also the sample solutions was adjusted to pH 12, and also the dose variations adjusting into the beaker glass at the variations 1,500 milligram per liters until 2,000 milligram per liters, and then the solutions was fasted stirring at 3 rpm for 10 for a minute, and also for the slow stirring 50 rpm for 10 minutes, and also the solution was settled in 30 minutes, and the filtered was filtered with the fine filter peppers, And next, about the concentrations of the treatment was measures, which is used to calculate the dye removal efficiency. These slides about the procedures determinations the effect of pH solutions. The procedure will be similar with the previous procedure, which is the dosage, the effect of dosage, but the difference at the variations of initial pH of the solutions, which is ranges 7 until 14. This slides about the procedure of determination the effect of coagulation dosage, which is the procedure will be similar with the procedure determination the effect of coagulant dosage, but the difference at the variations of fast stirring speed, which is start from 200 rpm until 400 rpm. These slides about the data analysis. In the data analysis stage, we use ANOVA and also LSD test methods. The LSD test method was conducted when the calculated F values was greater than the F table values. This was intended to identify the significant difference between each treatment. On this slide, the curve shows the relationship between the coagulant dosage x-axis and the dye removal efficiency y-axis. In the study, the sample solution was adjusted to pH 12 because the literature indicate that the magnesium chloride performed more effectively under alkaline conditions. At this pH, the magnesium formed comprehensively as a magnesium hydroxide, although magnesium ion were also presented in a very small concentrations. Therefore, the magnesium hydroxide was likely dominant species responsible for the removal process. The dye removal efficiency at the concentrations of 1,500 milligram per liters lower than concentration 1,800 milligram per liters. This condition occur because the limited stoichiometric requirement at the low coagulant concentration, which resulted in sufficient site for co-precipitation. But when the concentration reached the optimum removal efficiency, which is at 1,800 milligram per liter, the amount of magnesium hydroxide had to provide a sufficient precipitation site to effectively bind the dye molecules. And however, when the coagulant concentration were increased, the removal efficiency decreased. These conditions occur because the active site of the magnesium hydroxide were saturated by the azo dyes, so the remaining magnesium hydroxide dispersed in the solution again and was detected during analysis. This is the figure results about the determinations of coagulant dosage. On this slide, the curve shows the relationship between the pH solutions x-axis and the dye removal efficiency of Ramasol UFG y-axis. Based on that figure, the removal efficiency was relatively low in the pH range 7 until 9. According to the literature that I had read before, surface charge and the species distributions of the magnesium exhibits a positive charge at the pH 6 until 11 and neutral at the pH 12, and the negative charge at the pH 13 and 14 based on the zeta potential value. This low efficiency occur because the positive charge on the magnesium had limited ability to remove from azoyl Fg. Furthermore, magnesium hydroxide at this pH didn't form, which resulted in sufficient surface area being available for dye to co-precipitations. However, the removal efficiency increased dramatically at the pH 10 until 12. The magnesium hydroxide compounds were from which were highly dominant compared to magnesium ions that tend to have very low concentrations. Therefore, when the solution was at pH 10 until 12, magnesium hydroxide with large surface area interact to form hydrogen bonds with the sulfonate groups of the dyes, while the magnesium ions also interact to form electrostatic bond with the dye. So at the pH, the process was still influenced by these two phenomena. Nevertheless, when the pH was increased to 13 until 14, the removal efficiency decreased significantly. This phenomenon occur because the magnesium hydroxide surface become too negatively charged, which create electrostatic repulsion with with the negatively charged of the sulfonate group. So, consequently, the dye disperse back into the solutions. These slides about the figure results of the determinations of the pH solutions. On this slide, the curve shows about the relationship between the coagulation speed x-axis and the dye removal efficiency of Ramazol yellow FG y-axis. Based on that figure, at the lower speed 200 until 250 rpm, the removal efficiency was lower than at the 300 rpm. These conditions occur because the low coagulation speed cause inadequate coagulant distribution in the solution, resulting in a poor interaction between the coagulant particles and dye molecules. The optimum conditions occur at the speed 300 rpm because the speed provides sufficient coagulation energy to create effective collisions. However, at the excessive speeds 350 rpm until 400 rpm, the dye removal efficiency decrease. These conditions occurs because the excessive shear force at the high speed, which broke apart the previously formed flux. This is the figure results about the variations of coagulation speed. These slides about the conclusions and also the recommendations. The conclusions of this study demonstrate that all three analysis parameters had a significant effect of the removal efficiency of Ramazzola FG, reach average removal efficiency at 96% for each respective parameters, and also for the recommendations of this study, based on the results obtained, the transition metal salts are more recommended as coagulating agents compared to alkaline earth metal salt because alkaline earth metal salt shows a greater tendency to create co-precipitation absorption phenomena compared to coagulation's process. Furthermore, additional analysis is required for further parameters that influence removal efficiency to provide a more comprehensive understanding of the treatment process. This slide about the reference that I use for these presentations. That concludes my presentations. Thank you for your attentions and considerations. Good morning, good afternoon. Terima kasih.